Welcome everyone to the afternoon session. So very pleased to have our first speaker will be Lucas Calixto from Federal University of Minas Gerais. And he's going to speak to us about Harish-Chandra modules for map superalgebras. So when you're ready.
Okay, thank you, Jethro. So good afternoon, everyone. So if I'll start by saying that if one have any question, please just unmute the microphone and speak, because I cannot see the chat when I'm looking at my screen. Okay, so this talk I'm going to talk about representation theory of Lie algebras, more specifically of some classes of infinite dimensional Lie superalgebras. So these Harish-Chandra modules that I will introduce. And this is a joint work with Slava Futorny and PhD students of his, Henrique Rocha. And it can be found on the archive. So this paper, if someone has interest in looking in the details. All right, so here's a small overview of the talk. So the goal of the talk is to obtain a classification of all simple Harish-Chandra modules for basic classical map superalgebras. And I also would like to apply the results to obtain some family of modules over affine Kac-Moody Lie superalgebras. So this is the main goal. So I will start by recalling what is a Lie superalgebra for those which are not familiar with the subject. And then I will go through and talk about this tensor product theorem and introduce parabolic induced modules. This will be very important to the classification, and also the cuspidal modules. And finally, talk about the classification of Harish-Chandra modules in the context of map superalgebras and some applications to affine Kac-Moody Lie superalgebras. Right? Okay, so throughout the talk, the base field will be the complex numbers. So every algebra, every vector space will be over C. And okay, so what is a Lie superalgebra? So a Lie superalgebra is a Z2 graded vector space. Also, people call this a super vector space, which is just a Z2 graded, nothing else. And it has a bilinear multiplication, which is denoted by these brackets. And the brackets satisfy some superversions of the usual conditions of the usual brackets of Lie algebras. So the first condition, the first property is saying just that the bracket is well behaved with respect to this grading here, right? The second and the third one are superversions of the anti-symmetry and the Jacob identity, right? So if you look at the formulas, you see that what is new everywhere, and this is what makes superalgebras what they are, is this sign. So every time we'll have a sign which depends on the parity of the elements. So this A and B between bars denotes the parity of an element. So if some element is in G0, so the parity is 0. If some element is in G1, the parity is 1, right? So, okay, so these are the two superversions of anti-symmetry and Jacob identity. And two very natural remarks here is that if we look at only the even part, so this is going to be a Lie algebra. And the bracket is just this bracket here. It's just the restriction of this bracket, right? So because when you have only elements which are even, so you obtain precisely the usual properties of the bracket of Lie algebras. And the second observation is that the odd space, so this G1 bar, this is going to be a G0 module and the action is induced by the bracket. So here's the action, right? So for any x in G0 and y in G1, x acting on y is going to be just the bracket of x and y. So this kind of shows us how, more or less, how superalgebras behave, and what we need to understand in order to understand the structure of a Lie superalgebra. So it kind of breaks the problem of, okay, so I have to understand the Lie structure of the even part. I have to understand the G0 modulo structure on the odd part. And there is something that I'm not talking here, and it's not going to be important in this talk, is that when we restrict these brackets to the odd part, this is going to be a symmetric bilinear form. And this identity here is going to be some sort of property on this symmetric form. So this is the other ingredient that we need to understand in order to completely understand the Lie superalgebra, right? Okay, so but people that are not familiar with superalgebras can many times think about Lie algebras, and for what I'm going to say is going to work just fine. Okay. So let me say a few words of what is known and how was the story behind the classification of Lie superalgebras. So the classification of all finite dimensional simple Lie superalgebras over C, that actually over algebraically closed field of characteristic 0. This was obtained by Victor Katz in 1974, right? And the classification of all such superalgebras is it's kind of broken in pieces, right? So it's not as in the Lie algebra case. So here we have simple finite dimensional simple Lie superalgebras, and we have those which are the Cartan type, and we have classical, right? So this classical into this class of classical, we have the so-called basic ones. So this is the class that I'm mostly interested today, right? Because the reason is because this class of Lie superalgebras behaves very much similar to semi-simple Lie algebras, and we can use many ideas and results from the non-super case to this case. So in a few words, this is the starting point. If you want to study Lie superalgebras, the starting point is the basic ones, right? So these ones here are more hard, let's say, to study. Okay, so as I was saying, I'm going to restrict the talk to the basic Lie superalgebras. And so these guys here, they have Cartan subalgebras, they have nice root systems, they have Dynkin diagrams, and they have non-degenerate supersymmetric invariant bilinear form. So every concept that we are familiar in the Lie algebra case we have here. Of course, it's going to have many differences, but at least we have these kind of concepts, right? Okay, so let me give you a very basic, very fundamental example of Lie superalgebra. This could be kind of an SL2 in the super case. So this is going to be the SL12. So in terms of vector space, is just the matrix. This matrix is given by blocks, right? And so if you see here, we have A plus D, which are precisely the diagonal elements here. This is just saying that the super trace is equal 0. Super trace, by definition, is the trace of the first block minus the trace of the last block, right? So as you see, even the definition is very similar to the SL2, which are just the trace equals 0. Okay, so the even part is going to be this kind of matrices here. So we have 0 on this upper and down triangular part, and the odd part is going to be this direct sum of G1 and G minus 1, and G1 is just like this matrices, and G minus 1 is this kind of matrices. And there is a reason for me to write G1 bar as the sum. This is because I'm going to look at the structure of the G0 module over G1 bar, as I said in the previous slide. So if you see here, the G0 piece is just an GL2, right? It's a very, very natural Lie algebra. And when we look at G1 as a G0 module under the adjoint action, we have this decomposition. So we have this decomposition, and each piece of these guys here, they are irreducible modules over GL2, and this is just the natural module, and this is just the connatural module of GL2. By natural, I mean the natural action, the identity action, the identity representation of GL2. Okay, so and in this example here, we have this grading, right? So we have a grading here, and this grading is well behaved with respect to the Z2 graded, in the sense that the even part, the G0 bar is just G0, and the G1 bar is the sum of the even pieces here. It's just G minus 1, just plus G1. In this example, also, the Cartan subalgebra is just a set of diagonal matrices of G, right? It's just like a diagonal matrix of GL2. And we can define supersymmetric, bilinear, non-degenerated, and all the adjectives that I said in the previous slide here to be this bilinear form. So the supertrace. So A comma B goes to supertrace of A times B. And I want to notice that in this example, SL12, the Killing form would work too. So the Killing form in the usual sense. So you look at the, not quite the usual, but pretty much the usual. We would look at the supertrace of the adjoint of A times adjoint of B. So I'm saying this here because it's not always the case that the Killing form is going to be non-degenerating the super case. So this is a very, very a big difference already in the super and non-super case. So if you look at the classification of Victor Katz, for instance, he breaks the classification into pieces, and one case is precisely the case where the Killing form is non-degenerated, and the other case is the case where the Killing form is degenerated. Okay. So now let me introduce the main subject of the talk, which are the map superalgebras. Okay, so from now on, G is going to be a basic Lie superalgebra, and A is going to be a commutative associative unital algebra. So as I said in the beginning, everything over C, over the complex numbers. So now let's consider this space GA, which is going to be as a vector space. This is just the tensor product of G tensor A. And this vector space is what we call the map superalgebra associated to G and A, right? So as I say here, this is a map superalgebra, so it has to be a Lie algebra. So I have to say what is the bracket, and the bracket of this vector space is defined in this following way. So for X in G and A in A, so we define first of all this XA to be this simple tensor here, and then the bracket on these simple tensors is going to be just, we use the bracket of G, which we know because G is the superalgebra, so it's a well-defined operation. And then we just use the multiplication of A, which is also well-defined because A is a commutative associative unital algebra. So this is the bracket of this Lie superalgebra. So a remark here is why the name. So why we call this guy map superalgebra. And this comes from the following fact. So let's say that X is an algebraic variety whose associated ring of regular maps is OX, right? Then so this is going to be a commutative associative unital algebra, this ring of regular maps. And then we could do the same construction here. That's what we do. So if we consider this superalgebra, it's not hard to show that this is going to be isomorphic to the superalgebra of maps. In other words, the elements of this guy here are functions. So these are functions from x to g, where f is regular. So here we consider g as a algebraic variety as well, right? So in fact, this let's say abstract construction, it's a very concrete one in which the elements are in fact maps from two algebraic varieties. Okay, so if you see at the definition, it's quite clear that the dimension of this map GA, this map superalgebra GA, is in general infinite, right? Because in general, A is going to be an infinite dimensional vector space. And so that's the reason I said in the beginning that we're going to study representations of infinite dimensional Lie superalgebras. Another observation that we're going to use is that G itself can be viewed as a subalgebra of GA. It's quite simple. We just see we just identify G with G tensor 1 in this tensor product here. Any questions so far? So please be free to ask. Right. Okay, so let me give you some examples, which are very, let's say, famous in the literature. So when X is just C, right? So we have that the ring of regular maps is just the like C of T, polynomials in one variable. And then the map superalgebra, in this case, is called current superalgebra, right? So this algebra and the next one that I'm going to introduce, they are very important in the study of affine Kac-Moody Lie superalgebras. So when X equals C star, then the ring of regular maps is just the Laurent polynomials in one variable, and the map superalgebra associated to these two data here is called the loop superalgebra. So as I said, these two guys are important. The study of the presentations of these two classes here of superalgebras is important because it has many connections, for example, with the representation theory of affine Kac-Moody Lie superalgebras, and the representation theory of this kind of Lie superalgebras is very, very rich, and it has several applications in many branches of mathematics and physics. So the last example I'm going to give is when we take the n torus. So here we have C star times C star n times, and then the ring of regular maps is just the Laurent polynomials in n variables, and the map superalgebra associated to this data here is the multi-loop superalgebras, and this is important in the theory of toroidal Lie superalgebras, right? So all of these examples, they are subalgebras of this big algebra here. So in this case, affine Kac-Moody Lie superalgebra, in this case, toroidal Lie superalgebras. Actually, here is going to be a quotient, but here is a subalgebra. All right. So, okay, so now that I have introduced the algebra object, so I want to talk about representation theory of this. So let me introduce these Harish-Chandra modules, which appears in the title. Okay, so first I say that a GA module V is a weight module if V is a weight module when I look the action of G. So remember that G is a subalgebra of GA, as I said before. So every GA module can be viewed as a G module. So that's what I'm doing. So I'm just looking at this V as a G module. So I have a Cartan subalgebra. I can talk about weight spaces. I can talk about the weight decompositions. And this module V is going to be a weight module if we have a weight decomposition with respect to the Cartan subalgebra. So these V lambdas here are very familiar for many of you here, probably. And this is just the weight spaces, right? The support of a weight module is going to be all the functionals, all the linear functionals, so all lambdas in H star, for which V lambda is non-zero. Okay. We call V a finite weight module or a Harish-Chandra module. So these are just two names for the same thing. So V is a finite weight module if the dimension of every weight space is finite. So notice that I'm not saying that V is finite dimensional. I'm just asking for the dimension of the weight spaces to be finite dimensional. And actually, this is the most important cases. So the case where V is infinite dimensional, but the dimension of all these weight spaces are finite. We say that V is bounded if we can bound the dimension of every weight space by some number. So in other words, if there is some n, positive number, for which the dimension of V lambda is less or equal than n for every lambda in the support. Okay, so if you notice, we have a very natural example of a weight module. So GA is a weight module under the adjoint action. The weight spaces are just the root spaces. So the weight space is GA alpha is just G alpha tensor A. So because of these, we see that the root system of GA, which is by definition every element in the support which is that is non-zero, right? So the root system of GA is just the root system of G, right? Because if you see here, the alphas that appear in GA is just the alpha that appears in G, right? And so if you want to talk about the zero weight space, this is going to be H tensor A. So it's going to be the Cartan subalgebra tensor A. Just like happens in the Lie algebra situation, in semi-simple case. Okay, so in the super case, we can decompose the root system into two pieces. So we have the even roots and the odd roots. So what are the even roots? Are the roots for which G alpha is contained in G0 bar. And of course, similarly, we define the odd roots. And in the case, we have basically superalgebras, which is the case of the stock. Every root is going to be either even or odd. So we don't have roots that are odd and even at the same time. So if you go, for example, to the queerly superalgebra, this kind of stuff happens. So every root is even and odd at the same time. But here we don't care. We don't have this kind of things happen. Also, one nice thing that occurs here is that for each root, we have the dimension of the root space is 1. So again, just like in the semi-simple Lie algebra case. And therefore, we can fix a non-zero vector for each root x alpha. And we define the h alpha to be x alpha, the bracket between x alpha and x minus alpha. So, for example, if this root is even, and we take the subalgebra generated by x alpha, x minus alpha, and this h alpha here, so what we have is just an SN2, right? If the root is odd, then we have to be more careful. We will, in general, have different subalgebras. Okay, so what is known on the representation theory of GA so far? So the study of representations of this class of algebras started with Chari and Presley, and they classified all finite dimensional modules for loop algebras. So if you remember the example I gave, this is the case where A is the Laurent polynomials. Many works were done also in this case, but I just wanted to talk about the classification results here. And so Neher, Savage, and Senesi, they classified simple finite dimensional modules for map algebras. So here they consider A to be a general commutative, associative, unital algebra, not just the Laurent polynomials. So Alistair, myself, Adriano, and Thiago, we started the study of this these modules for the super case, and we classified simple finite dimensional modules over classical map superalgebras. So this is a series of 3 or 4 papers, because many times we have to consider kind of separately cases. Now, every guy here, we have finite dimensional. So in all these works, we study finite dimensional modules. And going to the infinite dimensional case, we have that Britten, Lemire, and Lau, they classify simple Harish-Chandra modules over map algebras associated to finite dimensional reductive Lie algebras, right? So in this case here, simple Harish-Chandra modules, as defined in the previous slide, they are not in general finite dimensional. They just have to have weight spaces which are finite dimensional, but the modules, they are infinite dimensions in general. Many other classes of modules and theory of extension between simple objects, block theory, and etc. They were studied before map superalgebras in recent years, like in this the 10 last years. So there are many works on this, the representation theory of this Lie algebras and superalgebras. Okay, so now let me start to go into the details to prove the goal that I stated in the beginning, which is the classification of Harish-Chandra modules in this case. So first of all, I want to start talking about a tensor product theorem. Okay, so very natural question. So let's say we have a G1 and G2, 2 Lie superalgebras, and therefore we can consider the direct sum, G1 plus G2, right? So this is, again, a Lie superalgebra. So what can we say about finite dimensional simple modules over this direct sum? So this is a very natural question. So in the non-super case, I'm going to state first what is the classification of modules over this direct sum. So for this, let Vi be a simple finite dimensional GI module. So in the non-super case, so assume that G1 and G2 are Lie algebras. So we have these 2 statements here. So first one says that if we take the tensor product of these 2 simple modules, then this tensor product is again simple over this direct sum. And moreover, any finite dimensional simple module is going to be of this form, right? So I forgot to give emphasis for this word here. So what can you say about finite dimensional modules over these? So in the Lie algebra case, it's a very nice question, a nice answer. So it's just you take 2 modules, 2 simple finite dimensional modules over these 2 Lie algebras, and you just tensor these guys, and you're going to get everything. Every finite dimensional simple module is going to be of this form. Okay, so in the super case. So in the super case, we have 2 possibilities for this tensor product. So it could be simple, it's fine, or there is a case where it's not simple, but it's not so bad, because in this case we have a submodule V. It's a proper submodule of the tensor product, and the tensor product is going to be isomorphic as a module over the direct sum of this same guy, right? So in view of this this result here, so we define this tensor with a hat, V1 tensor hat with V2, to be the unique non-zero simple submodule of V1 tensor V2. So in other words, I'm just defining this tensor product to be this V that appears here. In the case which is not simple, and in the case which is simple, it's going to be just a tensor product, right? And so the analog in the super case for this second piece here, which says that any finite dimensional simple module is just a tensor product, is going to be this one. So any finite dimensional, simple finite dimensional module over this direct sum is going to be a hat tensor product of 2 simple modules, right? And what's important to notice here is that this kind of phenomenon of appearance of this submodule here is due to the superversion of the Schur lemma. So the very famous Schur lemma here in the super case is not as nice as in the Lie algebra case, and because of this, we have this kind of stuff happening. So if you take two simple modules and you tensor these two guys, you can have a module which is not simple for the direct sum. Okay, so what about simple infinite dimensional modules over the direct sum? So if you see here, everything was finite dimensional. So what about this? Surprisingly, that there was no, we tried to find and we asked people, but it seemed that there was no result about these modules. So these are first kind of technical result in the article. So we proved that if VI is a simple GI module, also now I'm not assuming that VI are finite dimensional. Actually, I'm assuming just simple module. So if VI is a simple GI module, then VI V1 tensor V2 is again, we have a very similar result as in the finite dimensional case. We have that this tensor product is either simple or it's going to have a proper submodule for which the tensor product is just isomorph to direct sum of two copies of this submodule. And assuming that G1 and G2 are basic classical Lie superalgebras, that A1 and A2 are commutative associative unital algebras, then we have the analog of the second part here. Or precisely, we have this here. So what it says is that if V is a simple finite weight module over this direct sum here, then V is going to be the tensor hat of V1 and V2, where V1 and V2 are just simple finite weight modules over G1 and G2 respectively. And we also can say when this tensor product is in fact just when this hat tensor product is in fact just tensor product. So this is going to happen when we look to this endomorphism space, and if for some I this endomorphism here is just C, then the tensor product itself is simple, right? So this is this here is where the Schur lemma appears, right? Because who knows what for those who knows what Schur lemma says, we always have this kind of situation in the Lie algebra case. In the Lie superalgebra case, sometimes it can happen that this space is two-dimensional, so we could have some kind of odd endomorphism here. So these are the when this tensor product is not simple. Okay. Right. So any questions so far? Okay. Right. So now we have an infinite dimensional version of this tensor product theorem. So now we know how we can describe simple modules over this direct sum. It's going to be very important to the constructions. So now let me talk about induced modules. So I want to start with triangular decomposition. So a triangular decomposition, T of G is just a decomposition in this way. So we have three pieces, positive, 0, and negative piece. And these subspaces here, they are defined using a linear map. So here I didn't say what this Q is this is the lattice of the root lattice of G, right? So we just take the free module generated by the roots. Okay, so the positive part is going to be those roots, is going to be defined by those roots for which are kind of in the upper piece of the hyperplane defined by this linear map. So here is going to be those roots which are precisely in the kern of this map, and these are the roots which are in the negative part of the hyperplane. And a triangular decomposition of GA is just, we're going to borrow the triangular decomposition of G. So it's just a decomposition of this form here, where each piece here is defined using these pieces here. So I just answer each piece with A, right? So this is triangular decompositions. And we say that a triangular decomposition is proper when the G0 part is proper. So when the zero piece here is not the whole G. And we define also the roots which are obtained by this decomposition. So we have positive roots, negative roots, and we have this kind of zero roots, right? So we have a decomposition, triangular decomposition of G, and you also have a triangular decomposition of the system of roots, delta. Okay. So let's assume that T is a triangular decomposition of GA. Then for any weight G0, GA0 module, W, we can ask for the positive part to act trivially on W, and then we can just take the induced module. So again, for those which are, for example, had the algebra course, have seen Verma modules, for instance. So this construction here is a little bit more general than Verma modules, but it follows the same spirit of that, right? So these also are called generalized Verma modules by many people. Right? So we have this induced module. So now this is a module over GA, so over the map superalgebra. And in the case we start with W here, this module over the G0 part, which is simple, then it's not hard to show that this module here, it has a unique simple unique maximal submodule, and therefore a unique simple quotient, which we denote by LTW. Finally, so we have the kind of a reduction theorem. So if V is a simple finite weight GA module, so it's a Harish-Chandra module, then there exists a triangular decomposition. So we can find a triangular decomposition, which is going to depend on T, such that, so the vector space of GA plus invariance, so this is just as a vector space, this is just all the little V's on which this piece acts trivially. So this piece acts as 0. So this space of invariance is a simple bounded GA0 module. So here's the type, it should be T here in this. And so we have that this invariance, this invariant space is a bounded simple module over this 0 piece. And when we do this construction here, we obtain that V is isomorphic to this unique simple quotient of this induced module, right? So this is a reduction theorem, because now we kind of we are reducing the problem of classification of Harish-Chandra modules over GA to the problem of classification of simple bounded Harish-Chandra modules over this subalgebra, which is smaller in general, and it's easier to work on this. The key fact here is to look at the shadow of V. So the shadow of a module is a concept that was introduced by Ivan Dimitrov, Olivier Mathieu, and Ivan Penkov. And it's basically looking at how the root spaces act on V, and taking like roots which are injective, roots which are not injective. That's the main idea. Okay, so as I said, this is a reduction theorem. So now that we have this theorem, we are interested on classification of bounded simple modules over this kind of subalgebras. These kind of subalgebras are called the Levy subalgebras in many works. Okay, so we define V to be parabolic induced when V is isomorphic to one module, as in the previous slide, for some proper triangular decomposition. This is important. And we say that V is cuspidal when it's not parabolic induced. In other words, when I cannot find a proper triangular decomposition satisfying this. Right? And if the least superalgebra GA admits some cuspidal module, then we say that GA is cuspidal itself. So Now our problem then is to classify cuspidal modules over GA, because any other module is going to be parabolic induced from cuspidal modules via this theorem here. Some remarks is that if V is a cuspidal module, then the root vectors for associated to even roots will act injectively on V. And what is hard here is the action of odd root vectors. This is much more complicated, and this is kind of what gives you the main difference in the super and non-super case. Another remark is that when GA is cuspidal, in other words, when GA has some cuspidal module, then G is going to be isomorphic to one of these Lie superalgebras. So these are very nice Lie superalgebras. This is what I want to say here. So this is G is going to be isomorphic to one of these, or to a reductive Lie algebra with simple components of type A or C. And what is very important for us is that in any of these cases that appears in this list, the even part is a semi-simple Lie algebra, right? So this allows us to prove many results in a nice way. Okay, as I said, now I'm interested on classification of cuspidal modules. So let me try to classify them. For these, we are going to use the so-called evaluation modules. So let me describe what these are. So to construct evaluation modules, let's start with some maximal ideas. So M1 up to MR, maximal ideas of this commutative associative unital algebra, and pairwise distinct maximal ideas. So the associated evaluation map associated to these maximal ideas is just this composition here. So I just project, and then I use the Chinese Riemann theorem to get this isomorphism here. So now for any VI, a G module, and let's say the representation, the associated representation of this module is called rho I. So I'm going to now, using this data, these maximal ideas and these R G modules, I want to construct a new GA module. So for this, I'm going to consider the tensor product of these modules here, and the action of GA is going to be given throughout this composition of functions. So I first will use the evaluation map, which I defined here. And here is just the usual action on the direct sum of G, R times, on this tensor product, right? So here you kind of can get a feeling of where I want to use this tensor product theorem, because here you see I have a module over the direct sum of G, R times. So this was the main problem in this case. So this is a representation. This composition here gives a representation of GA, and this representation is called evaluation representation. And why is that? So let me just say one word about this. So why evaluation? Because in the case, for example, A equals to C of T, polynomials, maximal ideas is just points. And this map here is in fact an evaluation on these points. So in this case, we have actually evaluation. So the corresponding module is called an evaluation module, and is going to be denoted by these. So this is just a short notation for this representation given by this composition here. So here I'm saying about the modules that we choose and the points, kind of. So the maximal ideas we choose. Okay, so as I said in the previous slides, let's assume G equals one of these Lie superalgebras. So I can do that because this is the case where G admits cuspidal modules. So in this case, we have this theorem. So any simple cuspidal bounded GA module is isomorphic to an evaluation module of this form. So what is this? So this guy here, this V0 is going to be some simple cuspidal bounded G module, and all these ones here are finite dimensional ones. So we are allowed to have only one infinite dimensional modules appearing on this tensor product. So this is where the bounded plays a role. So all these modules here are finite dimensional. This one is going to be some infinite dimensional module, and the M0, M1, and Mk are just pairwise distinct maximal ideals on max spec of A. Okay, so this gives you a classification of simple cuspidal bounded GA modules. And the proof here relies on the following key points. So using that G0 bar is a semi-simple Lie algebra, we can prove that this ideal is a radical ideal. Right? And using this, we can see any simple cuspidal bounded module as a module over direct sum of G, like a number of times. And then we go through and work and apply the theorem on tensor, or a theorem about tensor products at the beginning. Okay, so now I want to say some applications on some different classes of Lie superalgebras. These are the affine Kac-Moody Lie superalgebras. So let's recall the loop superalgebra that I gave in an example before. So this is just G tensor Laurent polynomials in one variable. And the affine Lie superalgebra, A of G, is going to be this central extension of loop superalgebra. So the C, as I said, this is a central extension of the loop. Therefore, the C is a central element. And the bracket here is given by this we have the same bracket of the loop superalgebra, but plus some additional stuff that depends on C. Okay. A very straightforward observation is that any AG module V on which C act trivially can be regarded as a module over the loop superalgebra, right? Because it's going to be a module over this quotient, but this quotient is precisely the loop superalgebra. So in the other direction, for any module over the loop superalgebra, we can just say to C act trivially on that, right? And then we're going to have a module over the affine Lie superalgebra. And if we start with a module over the loop superalgebra called V, this module over the affine superalgebra is going to be called V C equals 0. And then it's not hard to see that any Harish-Chandra module, so remember a Harish-Chandra module is in general infinite dimensional, but the weight spaces are finite dimensional. So using this fact that the weight spaces are finite dimensional, we can prove that any Harish-Chandra module over the affine superalgebra will have to have a trivial action of the center. So therefore, it's just a module over the loop superalgebra. And then we have this theorem here. So the assignment that maps an LG module V to the AG module V lower C equals 0 gives a bijection between the sets of isoclasses of simple finite weight modules of loop and affine Lie superalgebras, right? Isoclasses is so I have all simple representations of simple modules, and I want to consider two representations to be equal if they are isomorphic. So these are this relation, that's what I call isoclasses. And this bijection restricts to a bijection between the respective sets of isoclass of simple cuspidal modules. So the result is about finite weight modules or Harish-Chandra modules, but if I do restrict to cuspidal modules, then I also have a bijection. Right. Okay, so it's not that hard when we go to affine Lie superalgebra. So basically, this results saying that if you want to understand these Harish-Chandra modules over affine, it's enough to understand the Harish-Chandra modules over the loop superalgebra. So now let's make stuff a little bit more complicated, and let's go to affine Kac-Moody Lie superalgebra. So that's what I call the G hat here. And this is going to be an extension by a derivation of the affine in the previous slide. So the brackets is going to be basically the same from the previous slide, but now I have this D element, and here D and C they commute because C is still central element, but D will act kind of a degree, counting degree on this the usual simple tensors. And again, I'm interested on Harish-Chandra modules over affine Kac-Moody superalgebras of this kind. So Fora and Slava Futoni, they study cuspidal. They study Harish-Chandra modules over this kind of Lie superalgebras, and in particular, they prove that.
Sorry, just a reminder about the time. Now it's 2:50 now. So
yeah, I can go. Oh, right. So I have a 2, 3, right?
Yeah. Well, maybe another 5 minutes.
Oh, okay. So right.
So okay. We have some time.
Yeah, I'm almost done here.
Okay.
Okay. Thanks. Okay, so they prove that any cuspidal G-hat module must be of level 0. Level 0 means that the little c, will act trivially, right? And so what I want to do here in this last 5 minutes is to construct a family of cuspidal modules over G-hat using the modules we have for the loop superalgebra case. So for this, we start with any module over the loop. And for this module, we're going to construct a module over the G-hat. So the vector space is going to be this tensor product, right? V and the Laurent polynomials, and here we have the action, right? So as I said, the little c will act trivially. The D is kind of a degree counting guy, and here we have the action that comes from the loop case. And as a module over the loop, of course, this new module is going to have infinite dimensional weight spaces, because every weight space is going to be tensored with this infinite dimensional space. But when we look at the action of D, which is the addition here, we have a nice decomposition. I'm not going to the details of this decomposition, but what matters is that this module is going to be a Harish-Chandra module if we start with a Harish-Chandra module in the first place, right? And to construct a family of modules over the affine, I want to start with some V0, Vk, some cyclic weight G modules generated by some weight vectors V lambda i's, some points. So remember, these are kind of the maximal ideals in the case of loop. Some points which are distinct pairwise, and we define a homomorphism of the universal enveloping algebra of the Cartan piece into the Laurent polynomials. So it's not, don't need to worry about the formula here, but it's important that Chari proves that the image of these homomorphisms of algebras here, the image is a Laurent subring of these Laurent polynomials. And then we have this result. So first of all, so for A, any element of C star and a G module V, we can do the loop module, and this module is simple if and only if V is simple. In the case that this homomorphism is surjective, then when we do tensor products, so and take the loop module associated to this tensor product, actually evaluation module here. So we have evaluation module, and we have the loop of this evaluation module. This is going to be cyclic. It's cyclic, and it's generated by precisely this this vector here. So it's just tensor products of these guys here. And if we start with lambda 1 up to lambda k, some elements in the dual of the Cartan subalgebra, associated to each of these linear functionals, we have finite dimensional modules over G. And if we take V0, any simple weight module, and A0, some element which is not equal to these little a1s, which appears here, then we can do the evaluation representation associated to this data, and we can take the loop module associated to this data, and this is going to be simple. So again, have to use that this is a surjective map. the last result I want to talk is what happens when this is not surjective. So as I stated before, Chari proved that when it's not surjective, it's not so bad. It's going to be a Laurent subring. And therefore, in this case, we have this. The image is going to be a Laurent subring. And we have these generalizations of these previous results. So first one says that one vector is not enough anymore, but it's not so bad. Just take these r-1 vectors, and this is going to be a module generated by these guys. It's not going to be simple, but again, it's not so bad. It's going to be a direct sum of cyclic modules. And the last case, here we have simple, right? We have this loop module was simple. The same construction now is not going to be simple, but it's going to be completely reducible. So we have a direct sum of simple pieces, right? And these simple pieces here, they are very, very concrete described. They are, we know how to describe these guys. And I want to finalize saying that our classification then implies that our classification of modules over the map superalgebra implies that any bounded cuspidal module over the loop superalgebra is going to be an evaluation module of this form, right? Where these A's are just pairwise distinct points, these F lambda I are finite dimensional module, and this V0 is just a cuspidal module. And the previous theorem provides a family of simple bounded modules over G hat. So these guys here. So we have a family now of simple modules over G hat. And in the case of Lie algebra, it's a statement of an unpublished work of Ivan Dimitrov and Dmitry Grancharov that these modules are precisely all the simple cuspidal modules over G hat. So we kind of believe that this is going to happen also in the super case. So in other words, these guys here gives a complete classification, but this is not proved. Okay, so we'll stop here. Thank you.
Okay, let's all thank the speaker. Very interesting talk. Are there any questions? Perhaps we have time for one quick question. Has any question raise their hand, perhaps? Okay, well, maybe let me ask then. So I was intrigued by this classification of cuspidal Lie superalgebras. Where does that come from?
It's
yeah, there. Have n going between 2 and 6.
Yes, exactly. Yeah, so it was. I think it wasn't work. It was published. The article was published in 2001, something like this. And this
was this Mathieu and those guys?
Exactly.
Okay.
Yeah. So they proved in this paper, they introduced this concept of shadow, which is very, very powerful. And they proved that the only subalgebras, the only Lie superalgebras which admits cuspidal modules are these ones here. Because these ones here, they were not new, right? So Olivier Mathieu proved already this fact, that for Lie algebras, the only ones that could have cuspidal modules were type A or C. So the new piece of data here was these guys.
Okay. Oh, yeah. Okay. Not seeing any other questions here. Okay, so let's thank the speaker again.
Thank you.